Okay, this is the second video tutorials in explicit dynamics I'm doing that is in the present playlist. It is intended for people who are interested in transitioning from the Abacus CAE to the 3D Experience platform. And the reason being that the FEA solver uh, within the 3D Experience is actually the Abacus program. Now, I already did this problem in tutorial one, where an aluminum tube was being crushed, which was an aluminum tube which was fixed at one end was being crushed by an impacting uh, mass block. Okay. However, I modeled the mass block impactor with solid elements. And I mentioned that I will come back and do this thing, two more video tutorials. One of them is where the impactor is actually modeled with shell elements. And later on, video tutorial 3 is going to be where I use an analytical rigid surface in order to define the impactor. So this particular problem is actually taken from the site of a YouTuber down below, where he actually uses the Abacus CAE to solve the problem. But the one that I did in tutorial 1 is the one on the top left corner. In other words, the aluminum tube is modeled with shell element and the impactor with solid elements. The four edges of the left side of the tube are clamped, and the impactor has an initial velocity of 25,000 millimeters per second. What I'm going to do now is repeat the same problem, except that the impactor is going to be modeled with shell element, as you can see on the right hand side. There is an initial gap of 2 millimeters between the two parts, as it was in the tutorial 1, and the dimensions are taken from that source that I indicated, and they're indicated here. The actual thickness of this tube, I'm assuming that, sorry, of this impactor, this plate is 1.5 millimeter. The lateral and vertical dimensions are the same, but the thickness is 1.5. Since that is the case, I actually have to go and change the density properties, the density value in the steel block at the impactor, so that it gives you the total mass, same as the previous tutorial. Okay, so here it is. I mean, this this is the data in tutorial 1, but notice that I have taken the adjusted the density of the steel, so that when you calculate the thickness, or the mass of this plate based on the 1.5 millimeter thickness, it gives you the same mass. Okay. Now, this comment is made here, and that is, first I'm going to use exactly the stiffness of the steel as it was in tutorial 1, and I'll show you what happens. You will see that uh, when I solve that problem, the steel plate actually deforms so much that it really loses its equivalency to tutorial 1. So I will come back, but after I run it and show you what happens, increase the stiffness of the steel by 10,000 times. Remember, we are not interested in the steel, we are interested in the crushing of the tube. Okay, so we will do that later. First, I'm going to use exactly the same stiffness that I had for tutorial 1. Aluminum is the same data from the first tutorial. Basically, it's isotropic linear uh, uh, isotropic uh, bilinear plasticity. So I need two pieces of data. These are the same things that I used before. We are going to use general contact. We're going to use general contact, friction coefficient being 0.3, and everything else is default, and total duration is 20 millisecond or 0.02 seconds. Now, the the details of the meshing is going to be done with is shown here. Uh, so I'm going to be use S4R reduce integration. Now, of course, this for the plate doesn't matter, but I'm going to use S4R 4 node basic bilinear quad element with reduced integration, and these are the sizes. The size 10 millimeter for the plate is totally, uh, insensitive to that because you're not interested in the deformation of the steel plate. Okay, so let's go ahead and do that. Here is the interface, and let me start with an assembly. Okay, and I'm going to insert my first part, which is going to be the aluminum tube. Okay, so we're going to go right click, insert, 3D shape. This is the aluminum. This is aluminum tube. Let me actually rename these things so that this says aluminum. Aluminum. Okay. Yeah. Copy. And on the reference, same thing. It just makes it easier to find out where things are. There we are. And let's make it. So I'm going to double click on that. We want to create a surface, right? So we are in double click on this second line. You're going to go into generative shape design, which is exactly what I want because I want to create a surface. So on that vertical plane, I will sketch. Let me make a square here and dimension these things. So this is 100 millimeter. I'll change the unit so that I don't have to type the millimeter anymore. You can do that in preferences, you already know it. So exit, and I'm going to extrude this. So select the surface tab. Here's the extrude, and because I want to keep a 2 millimeter gap between the back plate and the X, what is that? I think it's the what? Yeah, YZ plane. So I'm going to extrude from -2 to 302. That'll give you a total length of 300 millimeter. The direction is wrong, of course, so let me flip the direction. And this is starting 2 millimeters away from the YZ plane, and it goes 302 millimeters, so it's exactly the length that I want. Why don't we apply the material properties now? So although it's the same thing that I had in the previous tutorial one, I'm going to do it from scratch. So we go to tools. Here's a create material, and let me call this thing aluminum. I'll give it today's date so that I can find it later on if I need to. September 23rd, 26, 2023. Okay, and say okay. And it's, oops, I lost my connection. Okay, I think I lost my connection, so let me go ahead and connect again. Because I didn't use the laptop for a while, that's why I got disconnected. Okay, that should take me back. Yep. Let me close this, start again. Right there. Aluminum. What do I call this thing? September 26, 2023. All right, so where is it? Let me do that thing by date. Sort by most recent. Right there. Okay. So we're going to apply to this part. Green check mark. Close it. Now we can go and input our data right there. Yep. Double click. Okay. So we go to structural, general, density. The units are ton per millimeter cube, and I told you for aluminum, the data was here. It was what is that? 2.5 e to the minus 9. So it's going to be 2.5 e to the minus 9 ton per millimeter cube. Very good. And then we go to abacus multiphysics, mechanical, elasticity. For I use the 70,000 standard 70,000 MPa for the Young's modulus of the aluminum. Poisson ratio is 0.3. These are the same values that I used before. And then we go to plasticity, metal plasticity, plastic, oops, right there. All right, so it's about Mises isotropic hardening. So we need 250 at strain, plastic strain of 0, which means yield strength, and then 300 at plastic strain of 0.1. Okay, and that's pretty much it. All right, so it's over there. You can see that. Now we're going to go to insert our plate. Okay, so right click, insert 3D part again. I'm going to change this thing to, call it wall, properties, or impactor. How about that? Properties. I'll call it steel impactor. Impactor. I don't know whether it's ER or OR, impactor, maybe. Copy, we go to instance, same thing, paste, say okay, and let's go and make it. So we go to 3D shape, on the YZ plane, I will sketch. The square, which is 120 by 120 millimeters. Okay, so this is 120. This is 120. Exit. And I want to fill this thing. So we are in generative shape design. Right now, here is the fill. Where's the fill? Let's see. There's the fill. It fills that, and it gives you the surface. Let's apply our adjusted material properties here. So we go to tools, create a material. This time call it adjusted steel, because I have to change the density. Remember, I have to change the density so that it gives you the total mass as in tutorial 1. We say okay. Adjusted steel, apply on the impactor, check the green check mark, and now we're going to input our stuff. So structural, general, density, and that was set. Okay, so the adjusted value is 6.24 e to the minus 7. Now remember, I came with this number because the volume of the steel plate, which is 120, and thickness of 1.5 times the density should give you the same thing that I had in the previous problem. That's how I came up with this number, 6.24 e to the minus 9. So 6.24 e to the minus, what was that, 9 or 7? 7. 7. Okay, good. And then abacus multiphysics, I'm going to use exactly the values that I used in the previous problem, not adjusted Young's modulus. So for steel is 210,000 MPa and Poisson ratio 0.3. Okay, and that's pretty much it. I'm not sure whether I actually put the correct uh, Young's the correct uh, Poisson ratio for aluminum. So let's check it out. Yeah, I did. Okay, very good. Before we do anything else, let's save. All right. So everything has been done. Now we're going to go to the structure model creation. This is to mesh stuff. Click on it. It's an empty FEM. We have to actually do the meshing ourselves. Okay. So let's go to mesh. There is the aluminum tube. So let's do that. This thing got into hide mode, so let me show it here, right there. You can see that. So we're going to use steel, surface quad mesh on that. The element size is 5 and mesh it right there. Now let's mesh this plate. So once again, surface quad mesh on that. Oops, okay, so let me cancel that. Let me see for a second where I am. Oh, you know what? I made a mistake. I didn't want this thing to be, I didn't want this thing to be at the part level. I want it to be at the assembly level. So look, no problem. Let me delete this. Let's go back to this part. We're going to do this thing the way I want it. So we go to the part. Oops. Okay. Let me delete this. Delete this. Okay, that's gone. So we go all the way to the top. Sorry, I should have been careful because I happen to be in the aluminum part. Remember, I wanted to check the uh, Poisson ratio. I was in aluminum part, so I go all the way to the top, and now we're going to go to structural model creation, empty one. Okay, and I want to include, of course, all of these. You say okay. Right, see, the difference is that before that mesh appeared in the part, I wanted to appear in the assembly. Okay, it is possible to go in the other direction too, but I rather not to. So I go here, surface quad mesh. For this, it was 5 mm mesh it. Okay, and now again, surface quad mesh on that plate. This one is 10 mm mesh it. Okay, we can see everything is meshed here. We have to have properties, so let's go ahead and do the properties. Click on the properties. Here's a shell. The first one is going to be for this, which is going to be aluminum, right? And the thickness is 1.5. Okay, there we are. This is the first one. This is aluminum. This was aluminum tube, plate, properties, aluminum tube, and then the next one is going to be the plate. We're going to use the same thickness. That's how I adjusted. Notice this adjusted steel, 1.5. That'll give you the same mass as the tutorial one. Okay, let's save this thing. Good. We're pretty much done here. So now we're going to go and we're going to go to our structural mechanical scenario creation. Remember, this will do finite elements, but you do not have the explicit solver in it. Here you do. Mechanical scenario creation. You click on it, and it says, well, first of all, this is something that I forgot to do in tutorial one. I used general, which is fine, but it is a structural problem. I mentioned that in the tutorial one. So I'll go to structural. And the finite element one is the one that I'm going to We did. We selected. Remember we created it right here. We say OK. Good. All right. So let's see. Let us go to procedures. We're gonna do explicit dynamic step. You click on it. It's gonna be a total of 0.02 seconds. Everything else is default, including advanced. The advanced, this is checked. It has to be checked. Of course it is checked. Say OK. All right. Now, notice that uh, in the explicit dynamic step, there is this, in this structure analysis case, there is this line which says element type assignment. So expand it, double click on it, double click on it. It says the type of element that is being used is four-noded shell element, but I want to reduce integration, so I'm going to change this to S4R, S4R, reduce integration. Okay. Good. So that takes care of this. Let us actually do the restraints and things like that. Why don't I hide this, hide the mesh? So right click, for example, visibility manager. I don't want to see my finite element model. There we are. It's easier if we hit this up there. Okay, good. Now, let's do the boundary conditions. This edge, that edge, sorry, clamp, this edge, that edge, these four edges. These four edges are clamped, okay? And yeah, we have initial velocity of 25,000 millimeters per second or 25 meters per second on this plate. So let's do that under initial conditions. This is the initial velocity. Select that plate. In the direction X, and the value is 25 meters per second or 25,000 millimeters per second. There we are. This is the initial velocity. Okay. Interaction. How these things, interact with each other. I told you I'm going to use general contact, so I go here to interaction. First, create a friction contact property. In other words, specifying the value of the friction coefficient. You click on it. It's called contact property 1. Why don't I call this thing my friction coefficient, my friction, just so that you can see this is just a name, my friction. Okay, and then click on the friction. Yeah, you click on this, select the box, checkbox, and you put your friction coefficient, which is 0.3. Everything else is default. Okay, and we say okay. And once we define the friction coefficient, then we go to general contact. All right. Okay, so first of all, I don't want default value. I want my friction data. My friction. See, this is very easy to miss because otherwise it uses no friction at all. And that's pretty much it. Include all surfaces and things like that's an overkill. In a simple problem like that, it's probably easier if you do surface to surface or stuff like this. But anyway, I do exactly the same thing that was done in the previous tutorial. So we say okay. Yeah, that's pretty much it. We don't need anything else. Yep, let's go ahead and run it. So we go to what is that? We are in simulation. First, we do a model and scenario check. That's okay. No errors, no warnings. Simulation check. I don't anticipate any problems here either. That's going to be fairly quick. There is a warning here, but it's not a big deal. Okay, this is done. And now we're going to run it. And say okay. It's going to be very fast, but there will be an issue, as you'll see in a minute. I clicked on this iterations tab so that you can see what's going on. There is a wall clock here, by the way. Notice that I basically started running this at 12:31. Let's say 12:31, and there's a wall clock here. I want to check that to see how it matches, how this column matches with the clock that I have at the bottom right corner. So wall clock started at 12:30 or 12:31. We'll see. And this is the true time in seconds. Probably that'll take about maybe 2 minutes, something like that, maybe even shorter. You're almost halfway through. Now we're at the halfway mark. 1 minute, and this is 12:32, as you can see. %69 done. Now, what other things we have here? This is the time increment that is choosing. Notice that they're very small. That's the whole problem with the explicit calculation. These are very small. That's why you have so many steps here, 32,000 steps, for example. That's the main difference between, one of the main differences between abacus, between implicit solver and explicit solvers. Okay? The implicit solvers, they have to do iterations. And this is done. So you can see that this is almost 2 minutes and this is almost 2 minutes. Okay, good. So let me close this. All right, so here's the situation. Notice that this is initially. You see, this sheet, this steel sheet is so flimsy as far as stiffness that it actually looked like that. If you animate it, you can see what's going on. Where is this? If you animate it, and by the way, no, let's actually slow this thing down to have a better idea what's going on. Speed, let's make it smaller. Close that. Close this. You can see what happens. This thing hits the tube and then bounces back, and there is a lot of oscillation taking place in the steel plate. This is why I want to go and adjust the stiffness or the Young's modulus of this steel plate, make it 10,000 times bigger so it becomes a lot stiffer and just does not act as a flexible surface, basically. So let me stop this. We go back to steel. Here's the steel impactor. Here's the material. Double click on that. Double click on it. Cancel. Double click on this. Go to the elasticity and make this thing 10,000 times bigger. which means I put, I don't know, 4 more zeros here. 1, 2, 3, 4. Say OK, and go back and run it. What did I do here? Oh yeah, right there. Okay, let's go ahead and run it. In fact, if we check it, it should be 10,000 times bigger. You can see that. Here is the steel. Double click on it. Let's check it again. Yeah, not there. Yeah, 10,000 times bigger. You can see that. Okay, good. Go back here and run it again. I'm not going to bother checking it for messages and things like that. I'm just going to run it and see what happens. Now it's going to be another maybe 2-3 minutes, maybe a little bit longer. We'll see. Okay. All right. Obviously, that will change the number of time step, and some, may take a minute or two longer, but we'll see what the effect is going to be. Now remember, if you're doing a simulation, full car crash simulation and things like that, then obviously there's a lot more components that are interacting with each other, and I mean, some of these runs for full car may run unless you're using a supercomputer. Even then, it could take maybe an hour or so. But anyway, these are very simple problems that we are doing, so that's okay. The only caution, the warning that I give people who use these explicit solver is that it never fails. It always runs. It always gives you colors. It always gives you a number. It's just that, do these numbers and colors agree with the reality? And that is a different ball game. It's just getting the stuff to run is not an issue. But whether these numbers make sense, whether these colors make sense, that is completely different, a different league. The purpose of these tutorials is not to assess accuracy, but to show you, if you, or maybe if you're already Abacus user, how does it change? How do things change when you go through the experience? Okay, the solver is the same, but the interface is different. The tricks and tips and things like that are different. But yeah, so you can see that actually adjusting that Young's modulus does change the how fast these things are going to go. But I mean, it's going, and it's not going to take very long. We are already at 30%. Maybe another 2 minutes, we'll do the job. And then I want to show you a bit of a, it's not a trick, it's really how to actually show specific, like I'm not interested in the steel plate at all. I'm interested in the aluminum tube. So I want to see only the stress distribution or the deformation of the steel tube or aluminum tube. How do you go about doing that in the experience? Right now, it's almost 4 minutes, and we are not even half uh, halfway through, almost halfway through. So what I may end up doing, if I feel that this is taking a long time, I will cut the video in during that uh, duration so that the video becomes shorter, but I will tell you exactly how many minutes it took as far as the wall clock is concerned. You can actually see it. So you know what? I'm gonna cut it off right now, and then when it's done, I'll come back. Okay, this thing took about 8 minutes to complete, so I'm back here. You can see that it finished. And by the way, the wall clock is right here. It's about 8 minutes, and you can also see the plot. Plot is the number of iterations uh, versus kinetic energy, but that's okay. So anyway, the point is that it ran, and I'm going to close this. Now look, if I animate this thing, you can see what happens. This, if you look at the view from the side, okay, so let's go to view from the side, from the right, there's the steel plate. It doesn't bend like that, and you can animate it. You can see it crushes the tube, okay? If you put it sideways, you know, after a while, of course, it bounces back. It's supposed to. Now, this is von Mises stress, but uh, what if you want to look at, for example, only the tube? Okay, so we're not interested in the plate. So what we have to do is, first of all, let's get created, right? Well, actually, let's go here. Show the display group dialog. Okay, so I'm going to create a display group, create a new group, okay? And I just want the aluminum piece. I don't want the steel, okay? And notice that down here it says press release to apply selection change. So selection change. So where is that? Where is that release thingy? So it's right there. It's unfortunately not release, replace. It's right there. You click on it, and there we are. And we say close. Right there. So you can animate it now. It shows you, the legend is over here. It shows you close that. It shows you the tube itself, okay? And if you want to see the whole thing again, let me actually change this thing to displacement. There's the displacement, okay? And there's the von Mises stress. Remember, we are not assessing accuracy here. And exit. If you want to see the whole thing back, just double click on it, display group, restore all. There we are, okay? One last thing, just to remind you, if necessary, you want to plot data as a function of time. So you go to plots. Here is the XY plot from history. For example, you can do, let's say, total kinetic energy. And there we are, okay? Let's say on top of that, you want to do strain energy. So again, you click on this. This one, this time you go to total strain energy, total strain energy. And because this box is unchecked, it does not deactivate this. It just adds it to this graph. There we are, etc. So these plots are very important because in explicit analysis, you want to make sure that you don't have any energies which are induced either by hourglassing or you know some other matters. Okay. We're not looking at those in these tutorials. Good luck. Remember, tutorial 3, I repeat the same problem, except that instead of meshing the indenter with shell element, I'm going to use analytical rigid surface.